All right, so coming full circle now, let's talk about 7.3, which is about assessing normality. So we looked at 7.1, 7.2, and said that if a variable is normally distributed, we can use the normal calculator in Statcrunch to compute probabilities involving that variable. But then we said, well, but how can we tell if something's normally distributed? And that's what we're going to talk about now in this section. We took a little detour into chapter 4 because the methods that we use to determine if something is normally distributed are similar to the methods that we use to determine if there's a linear correlation between two variables. In particular, what we do is we look at the z-score, right? And you'll notice that the z-score of an observation and the observation itself is a linear relationship, right? So the relationship between x and z is linear. So to determine if a variable is normally distributed, we can compare the observed values, right, the values that we observe, with the z-scores that we would expect to get if the variable is normally distributed. And if there's a linear correlation between what's observed and what we expect, then we say that the variable is normally distributed. The scatter plot of observed values versus expected z-scores is called a normal probability plot. And to make a normal probability plot in Statcrunch, we go to graph and then QQ plot. If you want the correlation statistic to go along with it, then you'll click on the little button that says add correlation statistic. Visually speaking, what we're looking for when we look at a normal probability plot is that the points should all be pretty close to the line, okay? Numerically speaking, we compare the correlation statistic that we get when we click on the correlation statistic button. We compare that to a critical value from this chart. And this is a different chart than the chart that we used in chapter 4. So just pay close attention to that, right? If you're trying to determine whether there's a linear correlation, you use the chart from 4.1. If you're trying to determine if something is normally distributed, then you use this chart from 7.3. Okay, so let me just run you through a couple examples real quick. This first one says the data below represent the time in seconds for 6 randomly selected races of a greyhound named Barbie's Bomber in the 5/16th mile race at Greyhound Park in Iowa. I've never seen a dog race before, but I think it would be fun. Anyway, we want to know, is the variable finishing time normally distributed? So to answer that question, we're going to go to graph. We're going to enter the data, of course, but then we're going to go to graph, QQ plot, and we're going to make sure that we add the correlation statistic. Okay, and let's see what we get. So I've already entered the data into Statcrunch. So here it is. This is BB for Barbie's Bomber. So there's her data, or his data. I guess it could be a male dog. Anyway, so Barbie's Bomber. We go to graph, QQ plot. We're going to select just the Barbie's Bomber data. And then I'm going to click on add correlation statistic. So I'm going to click that box. And we hit compute. And this is what we get. So again, what we're looking for is we want the dots to be relatively close to the line. So visually speaking, this looks like it could be normally distributed. It looks like the data could be normally distributed for sure. And then numerically, we're looking at this correlation. If you forget to click that box, then it'll still give you this scatter plot, this normal probability plot, but it won't give you the correlation coefficient. So if you're looking for the correlation statistic, then make sure that you click on this box right here, okay? But I'm getting a correlation of 0.974. So going back, we can write that down. R is equal to 0.974. And now we want to know if that's good enough. So once again, our correlation statistic here has to be better than the critical value on the chart. Okay, now the critical value depends on the sample size. We have 1, 2, 3, 4, 5, 6, right? We have a sample size of 6. So for n equals 6, the critical value that we have to beat is 0.888. right? So the critical value we have to beat is 0.888. 0.974 is bigger than 0.888, so that's good evidence to show that the data is normally distributed, right? So we say maybe for n equals 6, critical value is equal to 0.888. And then since 0.974 is greater than 0.888, right? Since R greater than critical value, the data is normally distributed. Okay, so there's that. So the answer to the question is yes, right? Right, yes. The data is normally distributed. Part B, if Barbie's bomber runs the race again, what is the probability that she would finish in less than 31 seconds? Okay, so we want to compute the probability that her finishing time is less than 31 seconds. Now, how are we going to compute that probability? Well, we know now from our work in part A that this data is normally distributed. And since it's normally distributed, we can use the normal calculator in Statcrunch. We go to Stat, Calculators, Normal. And if you think back to what we were doing in 7.1, 7.2, you know that at this point we're going to have to enter in something for the mean, and we're going to have to enter in something for the standard deviation. Now, since we don't know what the population mean and standard deviation are, the best we can do is to use the sample mean and sample standard deviation from the data that we were given. So I'm going to go to Statcrunch, and I'm going to figure out what the sample mean and standard deviation are. And I'm going to use those in place of my population mean and standard deviation. So again, I'm using the Barbie's bomber data. And to compute the sample mean and standard deviation, I go to Stat, Summary Stats, Columns, right? And I want the mean and the standard deviation. Okay. So that's so the mean is about 31.9, and the standard deviation is about 0.52. So I'm going to write those down. Okay. Right. So I wrote those parameters down. That's what I'm going to feed into Statcrunch. Now, in Statcrunch, I can use the normal calculator. So I'm going to go to Stat, Calculators, Normal. And I can say, all right, so the mean is about 31.9. And the standard deviation is about 0.52. And I want to know what's the probability that Barbie's bomber is going to finish in less than 31 seconds. Let's see. So there it is, right? 0.0417. Okay. So probability X is less than 31 is about 0.0417. I think is what we said, right? 0.0417. Yep. Okay. So that's that one, which is unusual, right? Anything with less than a 5% chance of occurring is considered unusual. So it would be unusual for her to finish in less than 31 seconds. And that makes sense if you look at the data, right? In none of the 6 races that we randomly selected did she finish in less than 31 seconds. So yeah, it makes sense that we're getting an unusual result here. Okay, but that's that. Hopefully that ties together the concepts for you so you understand why we took this detour to understand, you know, how to determine if something is normally distributed, right? Because if it is, well, then you can use the normal calculator to compute probabilities involving that variable. Let me just give you one more example of determining if a variable is normally distributed. This one says The following data represent the speed limits in miles per hour on 12 randomly selected roads in Montana. Determine if speed limits are normally distributed. Okay. So once again, I'm going to go to graph, QQ plot, add correlation statistic. Okay, let's see what we get. So once again, I've got the data already in Statcrunch. You can pause the video and enter it in if you want to follow along. I would encourage you to do that. But here's the data. So let's go to graph, QQ plot. We want to see if speed limits are normally distributed, and we want to look at the correlation statistic to do that. So hit compute, and looking at this, it doesn't look great, right? Like the dots, they kind of seem to be doing this weird thing, and they're kind of grouped together. So you have a bunch of dots up here and a bunch of dots down there. I think that's because these are the speed limits on like highways, and these are the speed limits within city limits probably. So you have these two kind of distinct groups, right? But the correlation is 0.89. That's actually not terrible. I don't know. Let's look at let's compare that to the appropriate critical value, right? So our correlation statistic that we're coming up with is 0.89. What's the critical value? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 observations. So for n equals 12, the critical value is equal to, for n equals 12, the critical value is equal to 0.928. So that's the number we have to beat. We have to be better than 0.928. Okay. And this critical value isn't, or this correlation statistics, it isn't quite going to do it, right? It's not quite big enough for us to say that the variable is normally distributed. So we would say, since 0.89 is less than 0.928, so this is our R value, this is our critical value. The variable, or we could say, maybe we could say speed limits. I don't know why I used quotes. We could just say speed limits are not normally distributed. Okay. And that makes sense. That makes total sense, right? Because again, you have a bunch of like in-city speed limits, and then you have a bunch of highway speed limits. So there's two groups. They're kind of bimodal. They're not normally distributed. Okay, so that's that one. Here's your homework assignment for 7.3. You have 3 whole problems to do. I think you can probably handle that.